So an incredibly powerful concept for solving problems is the idea that mechanical energy is conserved. But that only happens under one condition, and that is when the only forces that do work on an object are what's called conservative forces, so forces that are conserved. The one that you have to worry about in this unit here is gravity. So if the only force doing work on your object is gravity, then you can use the conservation of mechanical energy equation, which is what this video is about. But there are actually other conservative forces too. So you could be experiencing the electromagnetic force doing work on your object or the spring force. But in our course, we're just going to be looking at the only force that will do work on your object is gravity. If that's the case, then you can use the conservation of mechanical energy equation. That doesn't mean the object can't feel forces other than gravity. So the object can feel a normal force or a tension force, but the key is that those other forces have to do zero work. So the object can feel the forces, but they can't be doing any work. So here's an example, say, of a tension force that does no work. Let's say you have a pendulum. The tension force would be this way, but the displacement of that pendulum would be this way. That's 90 degrees to the tension force. So here, WT would be 0. The tension force is going to do no work. So this situation here, you could use the conservation of energy equation for that situation. But if you had this sort of situation here, maybe we've got a sled or something, and you're pulling it along with the tension force like this, and the displacement is this way. Well, here the tension force is doing work. So in this case, you could not use your conservation of mechanical energy equation. It wouldn't work here. In grade 12, you'll learn actually a little tweak to that equation, which lets you solve problems like that. But for now, we can only use our conservation of mechanical energy equation if gravity is the only force that does work on your object. All right, so what is this equation? That's very handy to use. So in general, it's just that your initial mechanical energy, so mechanical energy 1, that's like the mechanical energy at the start of the problem, is equal to your final mechanical energy, or really your mechanical energy at any sort of time 2 in the problem. Basically just mechanical energy is constant, is really all that is saying. So we could write that out in a little bit of a more expanded way. If you remember what mechanical energy is, let's just write down the equation for it here. It's kinetic energy plus gravitational, right? So that means that the initial kinetic energy, so EK1, plus the initial gravitational energy, EG1, will equal the final kinetic energy plus the final gravitational energy. So this is the total mechanical energy at time 2. This is the total mechanical energy at time 1 over here. We can expand this even more because you hopefully remember that kinetic energy is a half mv squared, and gravitational energy is mgy, or mgh, it's sometimes called. Now, probably the mass of your object isn't changing. We're going to be using this equation for situations like maybe a car driving down a hill, sort of in neutral or something like that. That would be a good situation where you could use this equation, or a roller coaster, or maybe a kid on a swing. Those kinds of situations, the mass of the object isn't changing. Right? The mass of the kid on the swing doesn't change through that swing. So we don't need to have an m1 and an m2, but the velocity clearly will change, and the height, y, will change. G, the acceleration due to gravity, is not going to change. The object is going to stay on Earth. We're not going to have anybody shooting out into space. It would be a different equation for that. So this EK1 is going to be a half mv1 squared. So mass, I don't need an m1 because the mass will stay the same, but v, I need a v1. EG1 is going to be mgy1. And that will equal your final kinetic energy, which is a half mv2 squared plus mgy2. So that'll be your final gravitational energy. And that's really the form that we often use our conservation of energy equation in. All right, so here's an example. Let's say you have a roller coaster. This is the behemoth at Canada's Wonderland. It's 70 meters above the ground at its highest point, and 2 meters above the ground at its lowest point. And the roller coaster goes 3 meters a second over that high crest. We want to know how fast is it going at the lowest point in the track. We're going to assume there's negligible friction. So what we need first is just to figure out if you're allowed to use the conservation of mechanical energy equation to solve this. So what you want to do is just pick any old moment in the track, right? The track is curved, it's weird like that, right? Here's the coaster, the roller coaster. What you want to do is draw the Freebody diagram at some random moment like this. There would be a normal force, right? And there would be a gravity force. Normally we'd say there's a friction force too, but we're told that friction is negligible, so we don't need to write a friction force in. And then we know the displacement. At this moment in time, the displacement would just be parallel to the track, right? So that's delta D here. What this picture tells you is that gravity is clearly doing work. So gravity does work. So there's some sort of a WG here, but the work done by the normal force must be zero because the normal force is 90 degrees to the displacement. So that means that yes, we can use the conservation of mechanical energy equation. So that ME1 equals ME2. So the rule for being able to use it is that gravity does work and any other forces that the object feels do zero work. So that's good. And you'd still be allowed to use it if there was like an electromagnetic force doing work or a spring force doing work. I won't give you any problems like that though in this course. All right, so now we need to draw our picture. Our pictures for these kind of energy conservation problems look a little bit different than they have for, say, forces problems. What you really need is a before state and an after state. Because you're trying to do this ME1 equals ME2 thing, sort of the initial mechanical energy equals the final kinetic energy, we really care about what does the roller coaster look like at the start. Maybe it goes up and down like that. And what does it look like at the end? So this is state 1 up here. So that's where we start. At the very beginning here, we have a few things we know about the roller coaster. We know its initial height, right? Y1 is 70 meters. And the other initial thing that we know is that it's going 3 meters per second. So V1 is 3 meters per second. Then over here, this is state 2, the lowest point. We know Y2 is 2 meters above the ground at that point, but we don't know V2. That's actually a required thing. So I'll put a question mark there for that one. All right, we are now ready to solve. So we've determined we can use our conservation of mechanical energy equation, so we get to write it out. Half mv1 squared, so it's your initial kinetic energy, plus your initial gravitational energy, will equal your final kinetic energy plus your final gravitational energy. Now, when you look at this equation, you might think, oh no, I don't know the mass of the roller coaster, so can I even solve this? Yes, you can, because look at this. There happens to be mass in every single term here. If you have mass in every term, you can divide every term by mass. Very handy trick. This only works if I have mass in every term, but that's true in this case. And that means the mass cancels out of every single term. It's all gone. So my equation simplifies to this. A half v1 squared plus gy1 equals a half v2 squared plus gy2. All right, we're trying to get v2 on its own, so let's move the gy2 to the other side. So I'll have a half v1 squared plus gy1 minus gy2 equals a half v2 squared. So moving that gy2 to the other side. Let's get rid of the half by multiplying everything by 2. So you can multiply that by 2. You can either multiply the entire side by 2 in brackets, or you can multiply each term by 2. Maybe I'll multiply each term by 2 just because that's kind of nice for canceling out the half here. That cancels out the half here as well, of course. And then we're going to want to square root both sides, right, to get rid of the squared on my velocity here. So I'll get v2 is equal to the square root of v1 squared plus 2gy1 minus 2gy2, all square rooted. Notice that this square root and that square do not cancel each other because there's adding in here. So you can only cancel a squared and a square root if there's no adding or subtracting underneath that square root. Let's plug in our numbers. So V1 was 3 meters per second. So 3 squared plus 2 times 9.8. Y1 was 70 minus 2 times 9.8 times your Y2 is 2 meters. Plug all that into your calculator. So 3 squared plus 2 times 9.8 times 70 minus 2 times 9.8 times 2, and then square root the whole thing. And we get 37 meters per second. So the fastest you'll be going on the behemoth will be at the lowest point in the where whatever it looks like, the roller coaster. So the lowest point, wherever that is, you'll be going the very fastest there, and the speed you'll be going is 37 meters per second, approximately. Not exactly, because we were assuming negligible friction, and in reality there's a little bit of friction there. So you'll actually be going just a little bit slower than that, because you actually will have some energy losses to friction. This energy conservation equation assumes that you have no energy losses to friction, and that's actually not quite true in real life, but it's actually a pretty good approximation, so we'll go with it. All right, let's say you have a kid on a swing, and at the moment when the swing is 2 meters above the ground, we know the total mechanical energy. The first thing we want to find actually is just the velocity of the child at that moment, which doesn't require conservation of energy. That just requires understanding that mechanical energy is equal to the kinetic energy of the kid plus the gravitational energy of the kid. Now, because I kind of know where this problem is going, this is the initial mechanical energy. So this is really looking at a V1 and a Y1 here. I could draw a little picture of this. So here's the kid, there's the swing, and at this moment in time, their Y1 is 2 meters above the ground. So that height there, that height right there is 2 meters. And we know the mass of the child is 35 kilograms. We also know their mechanical energy. Mechanical energy is 1,234 joules. And we're trying to solve for their velocity. So we want to know V1. All right, so that looks like we're just going to take this general equation for mechanical energy and rearrange it for V1. So we'll want to move this term to the other side first. So mechanical energy minus mgy1 will give me a half m v1 squared. Let's get rid of the half by multiplying both sides by 2. Just do it out front here. Got a 2 times everything there. And then we want to get rid of the m. So divide both sides by mass, divide the entire side by mass here. Here the mass does not cancel because you don't have mass in this term, right? Mechanical energy, it's just mechanical energy, that's just one number. It doesn't have mass in there. So you can't cancel the masses there because you have mass in only one term here. But you can cancel them over here because there is just one term on that side. So what do we get? We get V1. We're going to have to square root both sides, right? So this is the square root of 2 mechanical energy 1 minus mgy1 all over m. And then you can plug in your numbers. So the mechanical energy is 1,234 joules. The mass is 35. G is 9.8. Y1 is 2. And all of that is divided by the mass, which is 35. So toss all of that into your calculator. So start with those brackets in there. So 1,234 minus the mass times 9.8 times 2. Multiply that by 2 on the top and divide by the mass on the bottom of 35. And square root that, and you should get a velocity of 5.6. It looks like 2 sig figs is good here. So 5.6 meters per second. So that's the velocity of the child at the moment when they're 2 meters off the ground. Now next, what if we wanted to know what's the maximum height that this child actually swings up to? Well, for this, we would need to use conservation of mechanical energy if we're allowed to, right? So we know that at some time, the child had this amount of mechanical energy, the 1,234 joules of mechanical energy. But what we don't know is, will that mechanical energy be conserved? Will that still be the child's mechanical energy when they're at the moment of their maximum height? To check, I need to draw a little Freebody diagram. So here's the child, there's the swing. They would feel a tension force, and they'll feel a gravity force. And their delta D at this moment in time is going to be following like a curve, right? But at this moment in time, their delta D would look like this. Notice that there's definitely a component of gravity that is parallel to delta D. So gravity does work. So there is a WG, gravity is doing work. But the tension force is doing no work, right? Because notice that FT is totally perpendicular to delta D. Those are my two requirements for being able to use the conservation of mechanical energy equation, that the only forces doing work on the object are conservative forces, which is just gravity. There can be other forces. There is a tension force on this child, but that tension force does no work. So you can use the mechanical energy conservation equation. So that ME1 equals ME2 equation. All right, then we draw our sort of before and after state picture. So the before picture, so state 1 looks like this. Here's the kid on the swing. We know they're in Y1 is 2 meters. We know their mechanical energy at this moment, which is really helpful. We know their mass the entire time, so I'll just put that at the bottom because that mass is not going to change. At the final position, the child is swung way up here somewhere, right? So this is state 2 over here. At this moment, we don't know their Y2. That's actually what we're required to find. But we do know their final velocity at that moment. Their final velocity will actually be 0. So if you think about a pendulum, when the pendulum reaches its highest point, it stops really briefly, right, before coming back down. So a pendulum is going back and forth. When it reaches its highest point, it stops. So the kid on the swing is essentially just a pendulum. When that kid reaches their highest point in the swing, they briefly stop and turn around and come back. So their velocity is 0. That's really helpful. All right, that lets us use our mechanical energy conservation equation. Now in general, remember our mechanical energy conservation equation is this: ME1 equals ME2. Now just based on what we're given here, it probably makes sense to leave the left side just ME1 and write this side as being sort of split up into its parts. So the kinetic energy, a half mv2 squared, plus the gravitational energy mgy2. And we know that v2 is 0 and y2 is the thing we're solving for. We know me1 is that 1,234 joules, and we know the mass is 35 kilograms. So we have everything we need here to solve for y2. So we just need to rearrange this equation for y2. So I'll do me1, the initial mechanical energy, minus that whole kinetic energy term here is mgy2. And then we want to get rid of the m and the g, so you can divide both sides by mg. That cancels it on this side. Notice the masses again don't cancel here because you don't have a mass in every term. There's no mass in the mechanical energy term here. So we can't cancel mass out. But we can plug all our numbers in because we actually have all the numbers here. Y2 is ME1 minus a half MV2 squared over mg. Let's plug everything into that. So mechanical energy 1 is 1,234 minus a half times the mass, 35, times the final velocity, which is 0. So that whole term is going to be gone. Divided by the mass, 35 times g, 9.8. So that's getting a little bit messy. So toss that into your calculator. So 1,234 minus 0, so that you don't have to write that in, divide by your mass, 35 times 9.8. And that gives me a Y2 of 3.6 meters above the ground. So that's the highest height that the child reaches on this swing.